Okay, friends, let's just start the lecture 18. So, we'll continue about our basic review of group theory. So, the last time we have been talking about the group axioms, which were essentially closure, associativity, inverse, identity, maybe one of these things. In addition, you can have groups which are, we said, discrete or continuous, or in both the cases you can have whether they are abelian, non-abelian. So abelian essentially tells you whether this whether the in the case of continuous group whether the generators commute with each other or the group elements commute with each other. Okay, so these were the topics we actually covered, and we started looking at SU2 representations and also the algebra of the SU2 group algebra. We looked at a little bit about discrete groups, which was needed. Essentially, we looked at Z2 and Zn groups, and we also mentioned briefly about non-abelian discrete groups which come at order 4. Essentially, order means essentially the number of elements. The continuous groups have infinite order, essentially because there are infinite number of elements which are possible, and that's the reason why they are given in terms of parameters which change continuously. Now we'll consider a very simple model today. We'll start with a simple model today, and then we'll continue with uh, what do you call actually then we'll continue with other things like meaning SU3 and stuff like that. But the model will the group we'll consider here essentially is the rotational group, which we are all familiar with. The rotation group describes the rotation of a vector in 3 dimensions. Say if you have a vector R, so let me draw it in some other color. So if you have a rotation R, vector R, okay, in X, Y and Z directions, okay. Now as you rotate the axis, say for example whether in XY plane or YZ plane or ZX plane, the length of the vector doesn't change, but the components of the vector get modified essentially. So the component of the vectors get modified. So instead of having, say for example, if you rotate in XY plane, you'll have something like X prime, Y prime, some angle theta. Similarly, you'll have an angle in the YZ prime and also in the ZX prime essentially. In 2 dimensions, if we just consider 2 dimensions, okay, so this rotation group is nothing but cos theta, sin theta, minus sin theta, cos theta. This is a group which is an orthogonal group of 2 dimensions, and it goes then by the name O2. O2. O2 is an abelian group. It's an abelian group. Okay, O2 is an abelian group, and every element in O2, okay, is orthogonal. That means, say for example, every element A belong to O2 implies A transpose is equal to A transpose A is equal to 1. Instead of a dagger, it's not a complex group, it's a real group. Instead of a dagger, you will have a transpose essentially. Okay, so that's the reason why it is different compared to SU2 group, or in 2 dimensions complex SU2 group, which has more than uh, uh, more generators compared to O2. So O2 has only one generator. We'll see it in 1 second actually. And how do you see that it satisfies all the group axioms essentially? Okay, you can check whether it is orthogonal or not. The simplest representation cos theta sin theta minus sin theta cos theta, and you can check that if you take the transpose of it and multiply it, it just gives me so it's an orthogonal group. Then you can also check the closure. If you multiply, let me call this as some rxy of theta. So if you have rxy of theta times some rxy of theta prime, another angle, if you multiply this, you can show it that it is equivalent to rxy theta plus theta prime. So it satisfies the group axiom law, and so you can show the associativity. Similarly, you can show this essentially shows you that it satisfies the closure law. In a similar vein, you can also show that it satisfies the associativity, and then you have an inverse, and the identity is nothing but the unit matrix. The identity is nothing but the unit matrix. Okay, so this sort of satisfies all the group axioms, and in 2 dimensions the action of rotations is abelian. Okay, so you have okay, you have r of x by theta times r of x by theta prime is equal to r of x by theta prime times r of x by theta. So the group is abelian. In fact, you can show that there is a one-to-one correspondence to O2 in the complex plane to U1, in the complex plane, the U1 group, which we have seen it so far. Okay, so there is only one generator in both the cases. Okay, this has also one generator. Okay, and there is also one generator in this case. So you can actually see that what is the generator for this thing. So the general definition for the generator you can just get it by expanding the exponential So for any continuous group, say for example, any continuous group element, say for example a of theta, r of x, y of theta is equal to exponential I theta dot x. Okay, so this is equal to so theta is equal to 0. So if you expand it for a small 0, okay, a of 0 plus I theta times x, okay, so small elements, and so on, so the generator can be defined as x is equal to minus I del a by del theta. For say if there are n number of thetas, you can actually, this is the most general, so you can actually expand it for any vectors, any number of vectors. So if you have generator kth generator, okay, at the limit theta k is equal to 0. So this is the generator of the definition of the generator. So you can get what the form of the generator easily. Okay, if you, the moment you, it is nothing but another formal way of writing. Formal way of writing the generators. So if you know the generators, you can actually write down what this is. So for O2, say for example, for the, okay, if we define it as O2, you can generally get it just from this essentially. So from this particular format, you can actually get it just from r of x y, r of x y. Let's expand it for small theta. Okay, for small theta, then we can easily see what it is, the generator. We could, there is other ways of doing it as well. Of theta is equal to unity plus, now the unity is this one, right? Essentially this one, the term which is coming from the cos theta term essentially. So unity is that cos theta term, okay, and then you have a small theta. The sin theta is just theta, so theta minus theta 0 0. So with this you can define your generator, okay, plus on other terms are there, so you are expanding around small theta. From this you can define your generator as x is equal to, now you can put an I, so depending upon what you want to put in, essentially, okay, you can define it with an exponential also, with an a complex, with an iota also, okay. So this will be a del r of x y of theta by del theta. Theta is very small, say for example theta goes to 0, minus 1. These is also the same thing, both of them, okay. Then if you want, you can put a 1 by I here, minus 1 by I or y. It's a smart, it's a sort of convention. So your x, there is only one generator. The one generator you have would be 0 minus I 0. So if you want, you can put an I here, so that Sometimes you put -1, okay, so that you can write, okay, let me just check. So this will become your r of theta xy is equal to e power I theta dot x. Just check whether I am writing it the I factors correctly or not. Okay, uh, I'm a bit slow with algebra, so I'm also a bit lazy. So just check. Okay, apart from that I factors and everything, signs of I. So this shows you that there is only one generator for O2. This is also true for SO2. SO2 is a special unitary matrix, okay, a special orthogonal matrix in which the determinant is also 1. Okay, this is actually true for SO2. In fact, the representations which I have shown are actually true for SO2. Okay, this is true only for SO2 because the determinant is 1 actually. Uh, so so what we have seen so far, and now you can see, okay, the point I was making is that in this particular representation, the determinant is also 1 actually when we took cos theta sin theta minus sin theta cos theta. Actually normally we take the minus sign on the 1 2 element. So the determinant, it's actually a representation of SO2 instead of O2. Now okay, now let's continue. So the point I'm trying to make is that if you have rotations in one plane, say for example in two-dimensional rotations, the group which is describes these rotations in a two-dimensional plane is actually a O2, SO2. Okay, it's an abelian group which is an SO2. Now the condition to derive the rotation group, okay, I assume that you all know a little bit more about rotations. So the point I was trying to make is in 2D rotations, what is the thing which remains constant? What remains constant is the length of the vector, which remains constant. How did you get end up having an orthogonal group is also because that the length of the vector remains constant. So what happens is if you have uh, the condition, if the length of the vector is r transpose r, this equivalents to r transpose prime r prime. So if r prime is equal to O, r, okay, some operation O is some operator, some symmetry operator. This symmetry operator preserves the length of the vector. This is very similar to what we had checked essentially in the complex space with Say for example, length of the ray, essentially length of the Hilbert space vector. So very similar that if you have ordinary rotations, so what it keeps is the length of the vector same. So this, if you substitute this, you end up having with O transpose is equal to 1. And that is precisely the reason why rotation group is always described by an orthogonal transformation. That is the reason why the rotation groups are always described by orthogonal groups. So the symmetric transformation should be an orthogonal symmetric transformation. So this is sort of easy. This is something which you all know in 2 dimensions. This satisfies all the group axioms and everything. You can also have a reverse rotation. Say for example, instead of rotating in the theta direction, you can also have the rotation in the minus theta direction. Where is the matrix? Sorry, where is the figure? Here. So instead of rotating in a theta direction, you can also rotate in minus theta direction and bring it back to the original. So there is also an inverse transformation which is possible. So this is quite nice and understandable in the case of 2 dimensions, and it's an abelian group. In 3 dimensions, you must have studied in your classical mechanics, but we'll just continue it there. Things become slightly complicated actually, because there are quite a few. The number of generators could be 3, because you can have so you cannot just not have a xy, yz, and zx. So a general rotation r, say for example, so if you have r, you can have rxy. Okay, let me just start in some sort of a standard notation. yz phi, z x psi rxy theta times r. Now r here is a 3-dimensional vector. So r is x, y, and z. So you can have 3 generic angles. General rotation can be expressed in terms of 3 Euler angles, essentially, like rigid body rotations. We'll use the same ideology, same methodology here. So where this entire thing is the generic rotation matrix, which we call it as, let's call it as OR. Okay, the OR is a combination of, say, RYZ, phi, or XZ psi, or XY theta. So this is a product of 3 where uh, let's write down what is the most general form, because I have expressed a generic three-dimensional rotation in terms of 3 Euler angles, or 3 rotations in 3 independent planes, and a product of these 3 gives you a general rotation. And the condition on this thing would be the same thing, like r prime transpose r prime is equal to r transpose r. This implies or transpose or is equal to 1. Now it is just that they are 3 by 3 matrices, so that's the only thing which makes a difference essentially. Now what are Rx, Ry? Rx, Ry we know. Ry z would be now 1 0 0 0 cos phi minus sin phi 0 sin phi. Okay, and Rzx is equal to psi cos psi sin psi sin psi 0 cos psi. Okay, Rxy is the same as this thing. So the generic rotation group is a product of 3 different. You can re-express entire thing in a generic rotation can be thought of as product of 3 uh, individual rotations, each in one particular plane. One in xy plane, one is zx plane, one is yz plane. That is a very interesting result, but let's not. We'll just take this to be honor. Now, what you'll have is corresponding to these 3. Okay, why we should have 3? Because so the entire point essentially is that you can express rotations in 3 dimensions in terms of 3 angles. That is because any orthogonal SO3 element. So that's because only 3 angles you would ask the question, because you can also have any number of angles, right? Why only 3 angles? Because SO3 has only 3 independent parameters. Okay, SO3 has only 3 independent parameters. Now, how do I know that? Because I can define that in an orthogonal group in 3 dimensions. Because if I write an orthogonal group, so in 3 dimensions, A11, A12, A13, A21, A22, A23, A31, A32, A33 times its own transpose times itself, and it's equal to 1 0 0 0 1 0 0 0 1. If you make this kind of approach, okay, this gives you the conditions. So these are 9 elements, near elements, okay, and this gives me 6 conditions. Okay, 6 conditions from orthonormality. So that gives me 3 free parameters. So that means that SO3 in 3 dimensions will have. So for example, SON would have. So you can just derive the general formula for SON. So how many would be the free parameters? n into n minus 1 by 2. So essentially that's what you'll get for S by n. Okay, so you'll have three free parameters, and these three free parameters can be adjusted in terms of three rotations, each in one particular plane, say for example xy plane, yz plane and zx plane, and the product of these three would correspond to a general rotation of this vector A R. And the rotation group, again, like I said, because it conserves the length of the vector, the crucial point is that it always conserves something, right? That's the reason why it's a symmetry group. So rotation group is also a symmetry group, the symmetry group which protects the length of the vector. Okay, uh, which protects the length of the vector, and that's the reason why it ends up being an orthogonal group. It's also a symmetry group. That's the reason we are studying anyway. That's the reason. Okay. So if you have three groups and the three, so there are three free parameters. So there are three generators. Each corresponding to this one. So you can readily express everything in terms of these generators. So you will have the generator for, say for example, xy plane would be, say whatever, meaning 0 minus I 0 if you write it in terms of the iotas, but let's just write it in terms of ones, say for example, just 1 0 0 1. Okay, so there is one generator, and then there will be the generator for, oh sorry, I am writing it for the two-dimensional one. I should write for the three dimensions case. Okay, so one would be in the xy plane, which we have seen 1 1 minus 1 0 0 0 0 0 0. And then there will be one in the yz plane, so that will also have, these are all off diagonal, traceless, Hermitian. Okay, and then there will be one in the xz plane. So you have these three generators. So SO3, any element G belonging to SO3 can be written in terms of e power I theta bar dot x bar. Now x bar essentially is, x bar is equal to x1, x2, x3, or whatever we wrote, no, yx, xy, yz, what these three notations. Okay, where, let me be more explicit, theta bar would be the, just using the notation here, phi, psi and theta. And x bar would be the generator corresponding to yz, zx and xy. xy. Okay, so with these three generators you have so you have an element of the group of SO3 expanded in this particular fashion. Now the point is that what happens if you expand it further, essentially that so for the first term would be the linear term. Say for example, so let's just expand the G. Let's see. Okay. So e power I theta bar of x bar. So this is a group element for you. So the first for small theta, exactly like what we did. For example, here that would be for two generations. Say when the xz we call it psi, right? So xz would be psi. This is psi tends to 0. Xy is theta tends to 0. This is phi tends to 0. Okay, in the limit, so the derivative term we wrote down. Oh, that's how we can derive this essentially. Now let me expand this. This would be the first term would be again 1 essentially, which is what is expected, plus I theta k or theta k xk, essentially sum over all the k, plus now what will happen to the second term? You know, when you expand the second term, it turns out okay, there will be uh, meaning you'll have theta I, theta j type terms, right? So theta I, theta j. So these terms will end up being something called end up being say theta I, theta j, meaning essentially uh, the coefficients of theta I, theta j. Now I can do, I'm just thinking if I should do the full now I can do, okay, what are these terms essentially? Now the point is that now if we have, say, okay, let's just do one thing. Okay, now we also know that e power I theta prime dot x bar will not change. The generators are independent of theta, right? Because we set them to 0. So if we have another group element, let's just do the group multiplication law. From the group multiplication law, what we need is that some what did we call OR of theta times OR of theta prime should give me OR of theta plus theta prime. Okay, now theta is three dimensional, so theta is a vector now, so this should be a theta bar and a theta bar, sort of. This is, what is this, theta bar. Now you want to do the same thing. Now expand this in terms of, say, expand this in terms of the exponentials. So for example, because O of R is essentially, if you remember O of R is what we call the total product essentially. This is what here is your O of R. Okay, so O of R we are writing in terms of exponential, right, of theta. So now if we write it in terms of e power I theta bar of x bar times e power I theta bar of theta prime bar of x bar. Now I know what is the x right hand side, essentially e power I theta plus theta bar of x bar. Now you equate both left hand sides and right hand sides, and when you do that, okay, I will leave the examples essentially. When you equate this thing, okay, when you do this equating the powers of theta, so if you equate the equal powers of theta on both sides, okay, you'll end up having something called the algebra, which is also called the Lie algebra. So what you end up is some relations between the uh, you'll end up having continuous relations with this one, essentially with the generators. So you'll end up having relations within the generators for non-abelian groups essentially. For example, for abelian groups there is typically only one generator. Okay, for non-abelian groups, when you do the equations of this particular type, you'll end up having conditions on uh, on the generators themselves, and which are given in terms of some coefficients, some numbers, and these numbers are called the structure constants. Okay, so the point is that suppose if you have a Lie algebra, Lie group, meaning, or I'll tell you what a Lie group is essentially in a second. If you have a continuous group like a rotational group, or similarly the complex plane SU2 or something, and if you express it in terms of these exponentials, that's what we have been saying, that it can be always be expressed in terms of exponentials in the previous graph. And if you apply the group multiplication law, and I have not shown the full thing because anyway it will be done in some other codes how it has to be meaning if you equate meaning how it will be the full thing. If you actually you can do it yourself. If you equate the powers of theta on both sides, you will end up conditions on the structure functions on the generators of the group, and these conditions are essentially expressed in terms of some commutation relations, and these commutation relations are called the Lie algebra. So the commutation relations between the various generators, and only if these commutation relations are satisfied, the group multiplication law is satisfied. Okay, only if these commutation relationships are satisfied, the group commutation law is satisfied, and this set of commutation relations is called the Lie algebra, and the constant in front of which appear in these commutation relations are called as structure constants, and this structure constant keep changing for each group. So for example, they are different for SU2, they are different for SU3. So for a given group, for SUN, for every n value SUN or S1, these structure constants are different. So every group, it has its own structure constants. Okay, every continuous group has its own structure constants, and once we know the structure constants, these um, relation meaning the group multiplication law is valid. Okay, and we know all the properties of the group. Essentially we end up having knowing all the properties of the group. So this structure the group is called a Lie group. Any continuous group of this particular type, where I can expand it in terms of a small parameter and write it in terms of exponential, is called a Lie group. And this the commutation relations between the generators of the Lie group are called Lie algebra. Okay, okay. So to summarize, Lie group, a continuous group which can be expressed as e power I some theta times x bar or something. So essentially the point is that it can be expressed continuously modified from unity. Okay, so continuously modified by unity. Okay, it can be theta of dot x plus so on so on, which can be expressed as this one. And Lie algebra is the algebra of this particular type xk xj is equal to I C K J L X L. So the structure functions are these numbers, and this is called Lie algebra. These are called structure constants of the group, and Lie group is this definition. So the groups, all the continuous groups which we are seeing so far, like orthogonal groups or say for example the unitary groups SU2, U1, they are all Lie groups. And for non-abelian groups like SU2 or O3, O2 doesn't have a Lie algebra because it's trivial, okay, because it's an abelian group. But a group like SU2 or SO3, which we are looking at right now, SO3 has a Lie algebra. Now we know that SO3 has a Lie algebra, right? Because there are three generators and all the three generators do not commute. So it's like if you go XY YZ rotation, that's not equivalent to YZ X. Meaning if you do instead of if you take an XY rotation and then do a YZ rotation, that is not equivalent to doing a YZ rotation first and then doing an XY rotation. Okay, so if you reverse, or if it is like if you reverse the trend, if you reverse the rotation pattern, you won't end up in the same place. That's the reason why this group is non-abelian. Okay, this group is completely non-abelian, and that can be seen in terms of this the generators, as the generators do not commute. Okay, the generators do not commute, and that can be seen just from deriving this group algebra, and which is also called the Lie algebra, and the structure functions are non-zero. Okay, the structure functions are non-zero. Okay, so the non-abelian nature of this entire group is sort of encoded in these structure functions, and that's an important point actually. Now there is also one more identity which the group uh, structure meaning generators need to satisfy. That is also called the Jacobi identity. It is some sort of a circular identity. Okay, it is like xj k so this is xk. So this is something called the Jacobi identity. So the generators of the group also satisfy the Jacobi identity. So what we have seen so far is okay. So let's just summarize the SO3. So this can be shown. Now we know these generators, right? For example, we know these generators of the SO3 group. So these are your three generators of the SO3 group. Okay. Now you can show that they don't commute, and you can derive their commutation relations. Okay, you can just check them that they don't satisfy this computation. They don't. You can derive their structure functions, structure constants, using explicitly what the form of these generators are for the SO3, and also you can show that they satisfy the Jacobi identity. So using the SO3 generators, uh, the explicit example of SO3 which we have derived so far can be shown to satisfy the commutation relations and to the Jacobi identity. So I guess I'll leave you both, meaning these two, you can check it in the homework essentially that explicitly this can be done. This will be one of the assignment 4 or something. You can show that this is the case essentially that they satisfy the commutation relations, and also they also give you the satisfy the Jacobi identity. So with this we have some idea about SO3 group. So to summarize, the SO3 group uh, preserves uh, preserves the length of the vector. It explains rotations in 3 dimensions. Okay, and this is a rotations in 3 dimensions are non-abelian in nature. So that means that if you rotate in, say for example, xy plane and yz plane, and if you want to reverse the order, say for example, first do the yz and then do the xy, it won't lead you to the same point in the xyz plane as a xyz say sphere. Okay, while they still keep the length of the vector invariant, they keep the length of the vector invariant. Okay, and that's the reason why the rotations in any n dimensions, essentially n dimensions, are always represented by an orthogonal matrix sum on depending upon the dimensions what we are considering of the dimensions of the vector. For 2 dimensions, it's an abelian dimension, and for more than 2 dimensions, it is a non-abelian group, which can be expressed in terms of, uh, for example, for each number of dimensions, you have to check how many free parameters you end up having, and accordingly, you'll have enough number of generators. So, for example, for O2, there is only one free parameter, and SO2, and that is only say they had that is the reason why it has only one generator. For SO3, coincidentally, it happens having that it is has 3 generators. For SO4, you'll have 6 generators. Okay. Similarly, you can keep checking essentially how many. Then there is a general formula how many you can have, because for an n by n matrix, you ask the question, n by n real matrix, you ask the question how many If it's an orthogonal matrix, how many free parameters you can have. With that, you can see how many free parameters are. For each parameter, you can think of one particular generator, and correspondingly, you'll have uh, n into n minus 1 by 2 generators. Essentially, the general formula would be given by that. And then, given the generators, you have the something called the Lia algebra, which essentially tells you how these generators interact with each other. Meaning, so if you know how the generators interact with each other, you know the so for example, if I apply xy rotation first and this yz rotation next, how does it change? So what is the difference? Because it's equivalent to some constant times yz rotation, right? Essentially, it's equivalent to some other rotation into some constant, essentially, and those constants are nothing but your structure constants. So if you understand the structure constants of this group, okay, the structure constants of the group, you understand the entire how this entire business of rotations applies on vectors in n dimensions. So, say for example, if you know as a structure constants as SO3, SU2 will not really have any structure constants because it only has one generator. SO3 you have three generators, so you'll have structure constants. Similarly, SO4 also you'll have several structure constants corresponding to six generators, and so on, so on, so on. So if you know the structure constants and the structure constants and the commutation relations, you understand all the properties of the group, and the structure constants and the commutation relations are extremely important. Only then the group will remain a group, because only then it satisfies the group multiplication law. Finally, there is also one more identity which is called the Jacobi identity, which has to be satisfied for the group to be called as a group. Essentially, the set of transformations should be called as a group. Good. Now let's go into the complex plane. So we understood sort of the real plane. In the complex plane, we already started off with understanding SU2 and U1 actually. So as I said, U1 is very similar to in the complex plane. So what we need in the complex plane is exactly what we have seen. So it conserves the mod squares of the okay. So instead of the transformations, also conserve the length of the vector, complex vector. Okay, so but it's no longer real vector, but it is a complex vector. That's what the rotations or whatever here it is essentially. For the U1, okay, for the U1 we saw that this is just z star is equal to mod z square is equal to z prime z prime. Okay, so this is what we have seen. This is already covered in previous lectures. So if you have a transformation z prime, so where z prime is equal to some u times z, okay, you have u dagger is equal to 1. Okay, so this is something which we already looked at. In the previous lecture. So now let's look at so SU2. Now the idea is now essentially instead of a vector which is a single number. U1 is a single number, right? Essentially, let's take Z1, Z2. Okay. Now let's ask that. Okay. So this, let me call it as um, some alpha. Alpha is equal to Z1, Z2. Now what I need is modulus of alpha, which is essentially Z1 mods the length of the modulus, essentially Z1 square, Z1 square, Z1 star Z1 plus Z2 star Z2 to be invariant, essentially. Okay. Okay. So alpha prime is equal to sum U Z1 Z2 alpha prime dot alpha, okay, is it should be equivalent to alpha dot alpha. That's essentially the point. That is equivalent to what I mean by alpha dot alpha is the length of the modulus of the alpha, or mod alpha such that so this alpha dot alpha is equal to okay, alpha dagger alpha is equal to, okay, this is equal to alpha prime dagger alpha prime. This again implies u dagger u is equal to 1. So everybody got this, that I wrote it down as alpha prime, the length of the vector I wrote it in terms of alpha dagger alpha. Okay, the length of the or it is essentially the length of the modulus of the complex vector in terms of this. So if I impose that the modulus of the any rotation, any transformation u, any transformation u, this is something which we have seen in the definition of the Wigner's theorem, that this will always be a unitary transformation, right? Essentially, so this will always be a unitary transformation because it conserves the thing essentially. So so for in the case of complex vector spaces, so the transformation is in such a way that the modulus of the vector space, the modulus of the vector or the is conserved, and this automatically leaves you not orthogonal transformations, but the transformation which preserves the modulus of the vector is essentially unitary transformation, which we have seen. So for two-dimensional vector spaces, like for example in the case of which we have seen the alpha, so we have the alpha prime is equal to u times z1 z2, and this gives me u dagger u is equal to 1, and u is a 2 by 2 unitary matrix. Now unitary essentially means complex, so we have seen again that if you have a complex matrix A, B, C, D, and which is unitary. So AB A star B star C star D star is equal to 1 0 0 1. So to start with, there are each the U has 8 elements, 8 real entries. There are 4 conditions, and another condition is coming is essentially if that U is equal to plus 1. So for any unitary matrix, the determinant would be plus or minus 1, but if I choose the sign of the determinant to be plus 1, so that gives me one more condition, that gives me 3 free parameters. So that gives me 3 free parameters. One second. So if so, what we have seen is that U is a 2 by 2 2 by 2 complex matrix which is unitary, and this is algebra we have seen earlier essentially that if U is a 2 by 2 unitary matrix, then UU dagger is equal to 1. That gives me so that gives me conditions. There are which are 4 conditions, and U in general has 8 real parameters or real entries, and then because U is a unitary matrix, its determinant could be both plus or minus 1, and we choose the determinant to be plus 1, and that gives me one more condition. So the total number of free parameters a unitary matrix in 2 dimensions is essentially 3 parameters. Okay, so if this again, so we end up with a case which is very similar to the case of SO3, very similar SO3. In fact, they are isomorphic groups, essentially these two groups. One is the double cover of the other. So if you have it's just that SO3 acts like rotations in real space, whereas SU2 acts like rotations in complex space essentially. Okay, so with this condition, we end up having with this condition we end up having three parameters, and these 3 parameters should reflect the some sort of rotations in the complex parameter space. Okay, so the U again in 2 by 2 case is we can derive the U in exactly in the same way essentially if it is represented by e power I theta bar dot x bar. Okay, and one can derive the generators of this group okay, the generators of this group, and the generators of this group don't, and they just end up being x is equal to x bar is equal to sigma x, sigma y, sigma z, the Pauli matrices. These are not rotations per se essentially, but okay, one can think of the they are essentially that if you look at the Pauli matrices, zero minus I 0, 1 0 0 minus 1 0 1 1 0. So these are again they look very much similar to the generators sigma x and sigma y look very much similar to the generators in some sort of a rotations in some sort of a plane, whereas sigma z is a diagonal generator, some sort of a diagonal, it's some sort of a labeling generator. So this is something new, so this is something different essentially compared to the other ones. So this is some sort of a diagonal generator, okay, which we use it for labeling, okay, which we use it for labeling. Okay, what I mean by that, and I'll tell you in a second. Essentially, that okay, you cannot while one is similar to the kind of uh, SO3, the form of the generators is not exactly the same in SU2. Okay, so they are very similar to each other, but the form of the generators is not exactly the same. Now, so SU2. Now you know what are the structure functions of SU2 also, structure constants of SU2. Also, you know. Because I know that epsilon I, epsilon j commutator is equal to I epsilon. So I know what the structure constants are essentially. Okay. So I know the structure constants of the group are known. I know that they satisfy the Jacobi identities. I know most of the properties because I know Pauli matrices very well. Okay. Most of the all the properties of the they also satisfy the Jacobi identity and so on. So essentially. So I know the group Lia Algebra of the SU2 is known. So they satisfy the Jacobi identity, they satisfy this commutation relations. I know the structure constants, and with this I know all the properties of SU2. I know it's a Lie group. I know almost everything. Now I am sort of ready to actually study the representations of this group. So, what are representations? Representations are I can build vector spaces which satisfy this uh, the group algebra or the Lie algebra of the group. Essentially, the representations which satisfy the group multiplication law. Okay, as long as they satisfy the group multiplication law, okay, they can be any dimensional, and I can construct essentially. You can have 3 by 3 with this. Okay. Uh, 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 okay. So with this, I think uh, we know that the all the properties of SU2 group. All we need to know is to construct what is called the representations. Representations are some which are representations are vector spaces. Okay, which satisfies the group multiplication law. That's it. Representations are vector spaces which satisfy the group multiplication law of SU2 or any other Lie group. Essentially, whatever Lie group you are doing, we can have SUN or whatever. Essentially, representations vector spaces which satisfy the group multiplication law, and they can be which is essentially the group multiplication law again is determined by the okay. Representations are essentially vector spaces which satisfy the group multiplication law. So they could be of any dimension. Allowed by the group. Okay, the group multiplication law. Okay, now to construct the representations, there are various methods and everything. One of the popular ways of constructing representations is essentially using. So, for a given group, say for example, you want to construct all possible representations. Say for example, so that essentially tells you that all possible um, what do you call uh, all possible vector spaces which can satisfy the same group multiplication law. For example, the case of say a spin. So what I'll tell you, I will do with SU2 in a second essentially. So there are several methods. One of the best methods which we use for unitary groups is essentially the angular momentum algebra. One of the easiest methods. Let me put this easiest in some sort of quote unquote because it's not exactly easy. Okay, is to use the angular momentum algebra. So one of the basic idea is that you use the same angular momentum technology and you construct all possible representations exactly like what you do in the case of say uh, the spin essentially. Okay, so let's just see, remember how it is done for SU2 essentially. Let's just do it for SU2 and then perhaps in the next lecture we'll do it for SU3. Okay, so what we want to do is construct the angular momentum eigenstates so that we can just use the entire technology of quantum mechanics. Okay, but for the group of SU2, essentially the spin group. Okay, 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 that's it. Okay, so now I'll just revise the standard angular momentum thing which you already know very well. And with that, I think we will sort of have an idea how to construct what these representations mean. Okay, Okay, what these representations mean. Okay, we'll come back to do that as well. Okay, so remember angular momentum algebra. So we have say for example mm, okay, so J is equal to, say for example, Ji is equal to sigma I by 2. Okay, the generators of, these are just generators of angular momentum. Then we have something called J square is equal to J1 square plus J2 square plus J3 square. Okay, this is an invariant operator which is called Casimir operator. So why it is called a Casimir is essentially that it commutes with, J square commutes with all the generators. So J square commutes with Ji is equal to 0, I is equal to 1, 2, 3. So J square commutes with all the three operator J's essentially, and that's the reason why. Then what you do, we use one operator as the laboring operator and the other operators as raising and lowering operators. So the diagonal operator J3 is used as the operator, whereas J1, J2 are used as the raising and lowering operators. So what we do is define J plus minus is equal to J1 plus minus I J2. So now we can define J square. So J square is also okay. We can write re-express everything. Now what is important is to see how J plus minus act on J3. Say for example, so J plus J minus is equal to 2J3. This is because J1, J2, J3 everything. Now J plus minus acting on J3 is equal to minus plus J plus minus. Okay, let me write it down neatly. So other thing which we have, just using the commutation relationship of sigma matrices, we get up with these relations. J plus J minus commutation is equal to 2J3, and J plus minus acting on J3, the commutator of J plus minus and J3 is equal to minus plus J plus minus. So if J square eigenvalues are lambda and J3 eigenvalues are m, sorry for my bad handwriting, let me write it down nicely. So what we have is J square acting on lambda m will give you lambda essentially because it's the eigenvalue of J square, and J3 acting on lambda m will give you m because that's what we defined essentially. Now what will happen if j plus minus acts on this lambda m? So j plus minus acting on lambda m is equal to some constant c plus minus of lambda m acting on lambda m plus minus. So that's the reason j plus acts changes m by 1 unit, j minus changes m by 1 unit. Essentially it goes, so j plus raises m by 1 unit. That's the reason why it's called raising and lowering operators. Lowers by 1 unit. Now for a given lambda, say for a given j square eigenvalue essentially, which is lambda, m is bounded. Okay, lambda cannot be, so essentially that lambda can be maximum equivalent to m essentially. So the eigenvalues are bounded. For a eigenvalue which is lambda, for a given lambda, say for example, okay, they can, lambda can be at most greater than or equal to m square. So you'll have lambda minus m square greater than or equal to 0. So this is bounded essentially. So there is a bound. Now, so because it's bounded, what we have, the condition is that if you take the highest value of say for example jz or m, essentially highest value of the jz eigen or j3 eigenvalue, which is essentially m, let's just take it to be j to be the highest eigenvalue of the, then j plus acting on it will go to 0. Essentially that's what it means, that j plus acting on it will go to 0. So then what happens is, if you, okay, so what I meant to say is, let, because it's bounded, say let j be the highest value of m. Then j plus acting on lambda j will equal to 0 because it cannot go further, so it's bounded essentially. Now if you act j minus on this, you will have the condition, okay, j minus j plus acting on lambda j. Now you know j minus j plus is, you can rewrite it as actually j square minus j3 square minus j3, all acting on lambda j. Now you can see what these conditions are, essentially lambda minus j square minus j acting on lambda j. Now this entire thing is equivalent to 0, so this means lambda is equal to j into j plus 1. So this is all what you have seen in your angular momentum algebra. So essentially, that if you have a j to the highest value, essentially lambda changes from minus j to plus j. That's what we are going to show essentially. So similarly, if you ask for the what is the small, okay, so lambda the j square value could be is j into j plus 1. Okay. Now similarly, you will have something in the slowest value. Okay, let j prime be the smallest value of m, then j minus into lambda j prime is equal to 0. Then we obtain, using the same analysis, j acting j plus and everything, this all implies that lambda is equal to j prime into j prime minus 1, where j prime j prime is the lowest value of m essentially, that means of jz. Now if you look at solutions which say for example, because lambda is the same value, right, essentially lambda should be for same lambda value of lambda for j into j plus 1 is equal to j prime into j prime minus 1. The only possible solution you will have is equal to j prime is equal to minus j. So this is what I was saying, that you can have essentially that you'll have things coming from so j prime j prime is equal to minus j. So you'll have m values taking from minus j to m takes minus j to plus j. Now you can also determine what the c values are. Okay. So now what you have is j minus j prime. Okay. Okay. Another condition you have. Another condition is j minus j prime, the lowest value to highest value, is essentially 2j because of this. So j is equal to an integer or half integer, because j plus or j man okay, j plus, let's just say j minus lowers by 1 unit. Just by the definition of what we not by construction, that you everything has to go by 1 unit, meaning if I act j minus on the state of containing j, so it should go as j minus 1. Say for example, if there is j minus acting on it, it goes to as j minus 1. Now j cannot be anything arbitrary. So j should go as j plus, meaning j either is an integer or a half integer. Okay, now you also have one more. Now we also have to determine the c coefficients. No, we have the c coefficient sitting here. Okay, this is in somewhere we have put the c's. Okay, here there are the c coefficients which are still undetermined. Okay, so let's determine them. Okay, so we the way we determine them is to sandwich them, find out what is this thing we have. Actually it can be shown, this you do it on your own. So lamp m acting on j minus j plus acting on lambda m, so it's the same state which I am sandwiching j plus, will give me c plus lambda m mod square. Now again we use the same technology, okay, because we have used c plus c minus. Okay, now we can also have, this is also equivalent to, it turns out, by using is equal to express the j plus j minus into the coefficients j square minus j3 square minus j3 into lambda m, that is equal to j into j plus 1 minus m square minus m. Okay, so we have, with this we have c plus lambda m. We can determine this thing essentially is that j minus m, j plus m plus 1 whole square root, and c minus lambda m is equal to j plus m, j minus m plus 1 whole square root. So for a given value of j, the states, okay, any state jm, this forms the m is equal to j minus 1 and so on, so minus j, so plus j to minus j, okay, minus j to plus j, this is the state. This forms the irreducible representation of SU2. So what we have used essentially is that we have determined all the properties of a given state in terms of angular momentum algebra. Okay, so we have determined its coefficients, we have determined its the representation, we have constructed the entire representation in terms of its j square values and jz values, and we saw that the jz values move from minus j to plus j, or m values, and j square value for a given j square value, essentially for a given j, we can reconstruct the entire this thing, and the dimension of this representation, the dimension of this representation is 2j plus 1. Now we want to actually work out, so what I mean by representation. The representation is also the generators, which are, so the generators, say for example j is equal to half, are just Pauli matrices. Generators for j is equal to 1 are Pauli matrices, which is 3-dimensional, say for example. Okay, so we want to use all this information. What we are using essentially is that, using the Lie algebra of the group and using our experience with angular momentum, we are constructing for any SU2 all possible representations for a given value of j, and j, if you remember, can take integer or half integer charges. Say for example, whether it can take it can take half, 1, essentially 3 by 2, then 2, so on, so essentially. Okay, so we have the dimension of the representation is 2 by 1, 2 plus 1. So we can use the relations j3 acting on jm is equal to m. This is which you have seen anyway. Now that we have already found out what these coefficients are, j plus minus we know acting on jm would be j minus plus m, j plus minus m, because we had determined what these are, plus whole square root j m plus minus 1. So with this we can really construct all possible representations. Now you can take any value for a given value, meaning for any value of j and m. Okay, you know that for a given value of j, m goes to minus j to plus j. So with that information we can really construct all possible representations. Okay, now for SU2, this is a very important representation which I want you guys to do it. So first example, j is equal to half, okay, and m is equal to minus half plus half. That's all it is. So j3 would be acting on half plus minus half, give me plus minus half, half plus minus half. Suppose if I represent plus half with 1 0 and plus half minus half with 0 1, this is the representation we use, is equal to 0 1. Then j3, this is the first representation we are going to see, using the angular momentum thing, is equal to half 1 0 0 minus 1. Now j plus acting on half would be what? It will be just 0 because there is no higher spin than that. Okay, but then j plus acting on half minus half would give me, again the center coefficient would just become 1 and this will just give me half. So j plus would have the representation 0 1 0 0, and similarly arguments will have j minus, which is essentially j plus dagger, will be 0 0 1 0. Now let's construct j1 j2. So j1 would be half 0 1 1 0 and j2 would be half 0 minus I 0. So the Pauli matrices, so these are nothing but your Pauli matrices divided by half. Matrices are the j is equal to half representation of the SU2 group. So in fact, because the matrix is also ends up being, because we are donating, so the vector space would be 1 0 0 1 with 1 by square. Okay, we normalized, you have to normalize them essentially. So when you normalize them, it just becomes 1 0 0, 1 by square root 2 will come. So this shows you the example in which the Pauli matrices are like you ended up having the representation of Pauli matrices. So you started, okay, so you derived for j is equal to half the Pauli matrices as the generators of the SU2 transformations. Okay, j or essentially the angular momentum algebra. So you constructed the vector space, which is essentially 1 0 0 1 vector space. You have to normalize it with 1 by root 2 1 by root 2. Okay, and then you so both the generators as well as the vector space are called representations. So they are called the j is equal to half representation. In other words, they are also called something called the fundamental representation. Okay, here the Pauli matrices are two dimensional, no? So the fundamental representation is the representation of the generators of SUN group is n dimensional. Essentially, if you have a n by n matrix, okay, the fundamental representation of SUN group is essentially is an n by n matrix. So for SU2 group, the generators are 2 by 2 matrices, so they form the fundamental group, fundamental representation. Sorry. So just to make a little bit separation, also let's just take the higher representation just to make things more clearer. So let's just take one more representation, which is essentially j is equal to 1. Now m takes values from minus 1 0 1 or 1 0 minus 1. So what? In this case, we'll represent 1 1 with 1 0 0, 1 0 with 0 1 0, 1 minus 1 with 0 0 1. Okay, there are three states and so on. So okay, you'll have this particular representations. There are three states, no, minus 1 0 1 essentially. Now in this case, what will happen if for J1, J2, J3? If you derive the entire thing, so J3 essentially happens to be 1 0 0 0 0 0 0 0 minus 1 and J1 happens to be 1 by root 2 0 1 0 1 0 sorry 1 0 1 0 1 0. J2 is 1 by root 2 0 I 0 minus I 0 I 0. So these are three-dimensional matrices. Okay, these are essentially three-dimensional matrices. J1, J2, J3 are three-dimensional matrices. So they are still SC2 representations, but three-dimensional. They are represented by 3 matrices because J1, J2, J3 satisfy the same commutation relationships as C2, 3. Still satisfy the same commutation relationships as polymatrices. So SU2 algebra, so essentially SU2 algebra. These just satisfy the SU2 algebra. Okay, there are no 8 matrices here. They are not three-dimensional 8 matrices which satisfy something other. Okay, they don't satisfy the other things. Okay, so we'll see some other examples. What is the difference between those things and so what we have seen in the so what we have seen today is essentially a way of using um, angular momentum algebra to construct uh, representations, okay, which are irreducible representations of an SU2 algebra. Of SU2 algebra, essentially, the technique we used is essentially angular momentum technique. So we constructed J square because J square is a Casimir and J plus Jz, which is the diagonal eigenvalue. So using these two, we constructed all representations, all possible representations for a given value of j. So for example, we consider j is equal to half, j is equal to 1, and similarly we can consider j is equal to 3 by 2. That will be four dimensional matrices because the dimension of the matrix, the representation is 2j plus 1. Okay. Okay. So in the next lecture, we'll start looking at SU3, and then uh, we'll see the differences between SU2 and SU3.